So first of all, I want to thank you for the invitation to this seminar. It was I don't know how it worked, but I kind of self-invited in a sense because I talked to Yonut. I don't know if he's here, but I wanted to, tell you guys a bit about these cotangent homotopies and hear your opinion about it. So I hope you get interested in this. Another thing before I start is that if at any point you have a question, just please interrupt me. Okay, so let's start with this. So the talk will be scheduled as follows. So the idea will be to speak about certain homotopies. They are called cotangent homotopies, but they are actually certain maps defined on a disk. And these arise from this object that is called the Poisson Sigma Model. So in a sense, we will be connecting this field theoretic thing, which is the Sigma model, with a more Lie theoretic that I hope everybody in this seminar is more familiar, which are algebroids and groupoids, in particular related to Poisson manifolds. So the structure of the talk will be like this. Okay, good. So the structure of the talk is like this. First, I'll do a short introduction in which I will recall what this Poisson Sigma model is and essentially the things that we will be interested in about this in this talk. Then I will detail, I give more detail about these singular homotopies and some associated triangles on a groupoid. And then I will mention some conclusions and further things. Okay, let's start with this. Okay, I will start with this introduction. So in this talk, we will be always thinking of a Poisson manifold that I think everybody knows. And in particular, we will be interested in the case in which the manifold itself is a coordinate space. So it's either Rn or some open subset in Rn. But and even in those cases, what we will be doing will be non-trivial. But I will comment in the end how things generalize to arbitrary manifolds. But so, in this introduction, let's think of an arbitrary Poisson manifold. So there are at least three things that we can do with this Poisson manifold that I drew in this diagram. First of all, we can try to quantize it. I will recall what this means in a second. Second of all, we can try to integrate it into a symplectic groupoid. And I think everybody is more or less familiar with this. And the third thing is to kind of plug it into this Poisson Sigma model, into a field theory. And these three constructions are related like this. Let me write here. So the quantization has a lot of information. If you forget some of those in a particular way, that it's called a semi-classical limit. And remember, in quantization, there is always a scale parameter, which is h bar. And in this limit, one considers h bar going to 0. So let's think heuristically. There are lots of information here. We take a certain limit in a particular way, and we should obtain a version of a symplectic group. It could be a local one, so that the structure maps are only defined for small arrows, or it could be a formal one in which you think of, let's say, formal arrows or a formal family of groupoids. And so this is this arrow. And this other arrow, well, it comes from the work, the combination of the works of Kontsevich and Catania and Felder. Which showed that if you perform a certain quantization here of this manifold. But in this talk, oh, it says that, do you hear me well?
Yes.
Okay, great. I just got a message saying that my internet connection is unstable. I hope it's not serious.
It's okay.
Anyway, just let me know if something goes wrong. Oh, but I should open, I don't know how I should open the chat. But anyway, so in this talk, what we are going to do is relate this directly. So complete, let's say, this diagram like this, and start with this field theoretic presentation and take the semi-classical limit directly from here to here. Heuristic. The thing is that here, the main computations involve heuristic integration over infinite dimensional spaces and so on. So many of the computations here are heuristic, but the end result, for example, Kontsevich star product, it's something well-defined. So again, using heuristic manipulations with these integrals, we will consider the semi-classical limit and arrive to something here. And then we will show, let's say, rigorously that these objects that we obtain produce what we expect from them. So let me be more precise in a second. I don't know if I should say a bit more about this. So let me complete this picture quickly. So a quantization of the Poisson manifold, it's a family of product structures. Typically, one considers a formal family. So this H is a formal parameter, and the product structure is some smooth functions enlarged into a formal power series in this parameter. This is M, sorry. And the idea is that, what is the relation to Poisson structures? This family of products is like this. It should start with the pointwise product. And then the first order correction should be given by the Poisson bracket. So you can think that this family is it's a deformation of the pointwise product of functions in the direction of the Poisson structure. Let's say this is pi. And then there are higher order terms. These higher order terms are needed for this thing to be associative. So you want this product to be associative in all the orders of H bar. Let me remind you quickly that this problem is a complicated problem. It's hard. And the things that enter in conflict is first that you want to, of course, the pointwise product is associative, but once you deform it, you really need to add more terms. Otherwise, it won't be associative. The lowest order identities that appear in associativity is one of them is the Jacobi identity for the Poisson bracket, and also the fact that the Poisson bracket is a derivation on each argument. But there are more identities that are not satisfied automatically, and then you need to add more terms. So this problem, to find such a thing, so given a Poisson bracket, find such a star product, it's a hard problem, and it was solved only by Kontsevich in 97. So, okay, let me say, I don't know if some of you might have seen a talk that I gave last week, but just to be very quick. So what about this? The idea is that if you consider, let's say that M, it's a coordinate domain. I'm trying to describe this semi-classical limit now. So you can think of linear functions. Linear. And having in mind, in the back of your mind's Fourier transform, what you can attempt to do is to compute this. So let's say P1, it's a function in M. And now I take this oscillatory exponential P1, and I want to do the star product with something of the same sort. And this is, the result of this is supposed to be, let's say, a formal power series in H and so on. And I evaluate this at a point X in M. The reason why you would do such a thing is because, morally speaking, because this is bilinear operation, the star product is bilinear. If you know it for these, let's say, kernels of Fourier transform, that you would know it for every other function, just by formally applying Fourier transform linearly. And okay, so what you expect from this, which is actually true for Kontsevich star product, is that this behaves like this. There is a factor here. So the result of this will depend on these two parameters, P1, P2, and X, and on H bar. So the behavior is like this. I call this SP. Again, it depends on these parameters. P1, 2, X. Okay, so this is the expected behavior, and you can verify it in the Kontsevich star product. And so what happens in this formula? I'm trying to describe this semi-classical limit, right? So in this formula, this term is regular as H goes to 0. Regular. Meaning that, okay, the limit as H goes to 0 is some function. It's okay, fine. But this thing, of course, if you think analytically, this is a complex number of modulus 1. And when H goes to 0, it kind of oscillates very fast, oscillate or turn round in the circle very fast. These are called fast oscillating symbols, and they are an object. I mean, they appear a lot in what is called semi-classical analysis and so on, in the non-formal case. But in any case, if you think of what would be the leading term in such an expression, it's clearly this term because it oscillates wildly. So this thing is what the semi-classical limit is considered to be. So this is the leading contribution as H goes to 0, and we think of this function as giving you the semi-classical limit, or at least defining it. Okay, so I hope this is more or less clear. And then what we try to do is, instead of taking a formula, Kontsevich's formula for this, and then trying to extract the semi-classical limit, we will do it directly from Cattaneo-Felder's formula. which expresses this, as I said, as a Feynman integral. So let's review this part.
So, Alejandro,
Yes.
so I don't see where the groupoid is.
Oh, yeah, thank you. I was describing the semi-classical. So what is where is the group point? Yes. So the point, what you can show is this. Because this object, this star product is associative, you can, associativity of this product translates into a bunch of identities for these objects, the A and the S. This S does not depend on H bar anymore. So in particular, S satisfies a quadratic equation that we will review a bit later, and says that actually SP generates in the sense of generating functions in symplectic geometry. So you take the differential and this defines an exact Lagrangian. So it generates a local groupoid structure, local symplectic groupoid. Well, I can't use the keyboard for some. Structure. It's a local symplectic groupoid structure where, so this I will call it GP. It's an open neighborhood of the cotangent bundle of M. It's a neighborhood of zero, the zero section here. I will review what this generates means a bit later, but in a sense, believe me that with this function, you can define all the structure maps for a local groupoid structure like this. So it would be over M, and it integrates the original Poisson structure. I hope this answers the question. Yeah, this was a good point. So this is the connection, right? So this arrow is like this. You start with the star product, you extract this semi-classical part, and because this was associative, this guy will generate a local symplectic groupoid. So yes, what we want to obtain is this guy directly from this field theoretic point of view. Oh, okay.
Alejandro, yeah, now it's clear.
You have another question?
I just said it's clear now. Thank you.
Sorry, I'm not hearing very loud.
I was just saying thank you. Thank you. And if it's
clear, okay. Yeah. Okay, no problem. I have to say that I don't use Zoom a lot, so completely lost control of who's speaking and where. And so I will remark this in a second. So I will come back to this remark. So there is a well-known relation between the Poisson Sigma model and what is called the Weinstein groupoid integrating. Oh, integrating M phi. But I will review this in a second. I first want to say something about the Poisson Sigma model. I think I'm going too slow, but okay. So let's think for, restrict ourselves to the case in which the manifold is some open subset in Rn. So this Catanian-Felder expression for a star product, it's like this. You take the two functions. Okay, let me tell you what these objects are. First of all, X. First of all, D is a disk, a two disk. So it's something like this. You can think of the standard unit disk in R2. There are three marked points in the boundary that we will use. Z1, Z2, and Z3. So now this big X is a map from the disk into M. And this eta, it's a field of covectors on M on top of D. So how do you write this? It's one form on the disk with values in a pullback bundle of the cotangent along X. So these are the two, they are called fields of the Poisson Sigma model. So one considers, let's say, all possible such fields. In a loose sense, the regularity and so on, for now, it won't matter. When we make things more rigorous, we will specify they will be smooth. It's infinity. But in any case, one consider, let's say, all possible such things. And this integral would correspond to the idea of summing over all possibilities. But each possibility comes with a weight. Well, the weight is like this. The leading contribution, again, will be this fast oscillatory part as h goes to 0. And this A is a functional that it's called the Poisson Sigma Model action. So all this structure comes by analogy, for example, with Feynman's formulas in quantum mechanics, in which you think that you sum over all possible paths, and each path comes weighted by the classical action of the path. So here is something similar. So just to say, this was discovered by Ikeda, Schaller, and Strobel. This functional. So here, you don't need to be in a coordinate domain to define this functional. You can define it for any manifold for maps like this. This is the pairing between dx, which lives on the tangent, and this guy that lives on the cotangent, and this is the bilinear form pi applied to this covector. And you use wedge product on the disk.
Sorry, Alejandro, there's a question in the chat what it means for A of X and eta to be 0.
To be?
To be equal to 0.
Well, eta equal to 0 makes sense. X doesn't make sense to be 0, but it makes sense to be a constant map that maps the whole disk into a particular point.
No, I mean, what does it mean when you have a value where the action functional is 0? Does that have like some other?
No, well, yeah, in principle, this functional, it could take positive and negative values. So 0 is not particularly distinguished. What is distinguished, and I thank you for the question, is in this kind of oscillatory integrals, if it was a finite dimensional domain, what is distinguished are critical points of this thing. So the critical points of this action, they correspond to, if you put X and eta together, you get a vector bundle map from the tangent to the disk into the cotangent. That's another way of seeing this thing as a vector bundle map that covers X from D to M. And the critical points correspond to the case in which this map is actually an algebraic morphism into the cotangent algebra. So algebraic morphism.
Yeah, that's what I was hoping.
Yes. So thank you. So those are the maps that are distinguished. In this sum over all possibilities, the ones that get distinguished a priori are these algebraic morphisms, which you would call a particular instance of some sort of homotopy, as we will see in a second. Let me say quickly, there is a measure in the space of all such maps, which is heuristic. So this is also heuristic, but it's dealt with some methods in field theory called Batalin-Vilkovitsky and so on. we will not care much about this now. But then what I wanted to say is that you're integrating over all possible such disks, and then you use the functions to take, let's say, as an expected value, as in probability. You sum over all possibilities and each, so you evaluate F1 at this point of the disk, Z1, F2 at this other point of the disk. And here there is a delta distribution, means that you only sum those disks that send this point into a particular point, little x, that appears on the left-hand side. So this is something, depending on the map, this takes a particular value, and then you sum over all of them, which the weight. So this is how you can understand this. Okay, this, and another thing that I want to say is that here the disk could be replaced by another surface. It's only that then it's not clear the relation to quantization. I mean, it could be something else.
Really an oscillator integral, right?
Sorry?
It's really an oscillator integral, right? It's an oscillator integral.
Yeah. This can be thought of as an oscillator integrals. You could then, for example, take stationary phase approximation, and this is what we are going to do actually.
Okay.
Yes. So let's think of this. Do you have another question?
It's a distribution then. It is a distribution.
Yeah, the problem, what is a distribution? The problem with this is that this space is infinite dimensional. And so as far as I know, there is no rigorous way of making sense of this integral, not even if you think of distributions. Because there are some things that I'm hiding. For example, the space where you are supposed to actually integrate is a subspace that satisfies something called gauge fixing condition, and these measures should be such that when you change this gauge fixing condition, the integral remains constant. So there are many things that I'm hiding that prevent the math to be rigorous. At the level of integrals, if you really wanted to think of this as an honest integral. Okay, heuristically, so let's continue this heuristic. So now, if I want to extract a groupoid out of this, what I said was that I should take the first function to be like this, the exponential of a linear, and take the second function of the same type and evaluate this at little x. So let's think a second what happens when I do this. So first of all, this will be e to the I over h. P1, let's say paired with this value at Z1. This guy will be the same thing, but at Z2. And another thing that I want to do, you see these exponents, they contribute to this exponent, right? So I will have e to the I. So here I will have a plus b1 x z1 plus b1 x z2. Okay. And then there is this delta. What I can do is think of, so in M, I can think of the delta as the result of a Fourier transform. So I integrate over P3, another parameter of this. Right? So I just enlarged the domain of integration. It's not only these fields, I also have this P3. So, and this, well, there is a sign here. So when I do this thing that I replace f1 and f2 by these exponential functions, and I change the delta into an integral, a Fourier transform, I get that the oscillatory exponent is actually this guy. So this whole thing, what appears in the exponent, I will be calling A prime. And morally, so what is the upshot of this? Is that if this was the path integral was a well-defined integral with oscillatory exponent, the semi-classical contribution that I was calling SP should be this A prime exponent restricted to critical points because of stationary phase, but not of A that gave us these algebraic morphisms, but of A prime. So this is how, let's say, the stationary phase works. The leading contribution of this integral is given by this function or functional restricted to its critical points. And so this is the upshot of this introduction. It was maybe too long, but so what do we extract from this? From this, what I extract is first that associated to, let's say, a coordinate Poisson manifold, I get two things that are actually well defined. First, this functional that I wrote very quickly here, but I will remember in a second, which is a well-defined functional. And second of all, the critical points of this functional translate into a, so these are the critical points, into a concrete system of PDEs that I will tell you what it is in a second. So this is what we extract from this heuristic consideration, a functional and, you know, its critical points. So let me very quickly say something that I omitted here. So there is a known also by Catania and Felder, another paper, the well-known relation between Poisson Sigma Model and groupoids, symplectic groupoids, that goes like this. If instead of a disk, I consider a square, and instead of doing this quantum type of computation, I do a classical Hamiltonian picture, then you arrive to an idea that one should be considering, first of all, what are called cotangent paths. So I is an interval, let's say 0, 1. So algebraic morphisms like this, these are cotangent paths. And also you arrive to an idea, oh, okay, what should I do? I think I'll let this ring. And you also arrive to the idea that among these paths, you should be considering a natural equivalence relation, which are called cotangent homotopies. Okay, so do you mind if I try to stop this ringing?
Please do.
Yeah, how do I?
Yeah, sounds good.
I just mute. Okay, it stopped naturally. Okay, so summing up, there are these things called cotangent paths, and there are certain homotopies called cotangent homotopies, which are algebraic paths like this, satisfying boundary conditions. For example, that along these directions, well, the linear part of this map should be 0. And so from this, it was noticed that if you take cotangent paths and you mod out by cotangent homotopies, this gives you at least a topological groupoid that integrates m pi. Suppose that this was integrable, then this gives you a symplectic groupoid integrating this that is called the Weinstein groupoid. And if you wanted to know how to multiply objects here in this groupoid, it comes from concatenation of paths. But I just want to draw, there is an alternative picture that you can do like this. So the blue parts are supposed to be 0 boundary conditions that correspond to, let's say, fixed endpoints in usual homotopies. And so here you take your, you want to compose objects in this groupoid. So you take one algebraic path that represent a groupoid arrow here in the quotient, another one. And if there is an algebraic map, so this would be an algebraic map from this letter y, this is a surface, right? Into like this. Then you can think that you are, at some point, these paths become very close and they concatenate. So this A3 would be it's homotopic to the multiplication of these two arrows in the Weinstein groupoid. Okay, so if you apply this idea, for example, to a Lie algebra, then you see this exactly the multiplication on the corresponding Lie group as arising from, let's say, flat connections on such a surface. So I'm just mentioning this because, first of all, it was known from before, and also because this kind of thing will appear in what we will be doing. I hope this is a relaxed seminar in terms of time. It is, okay. Also, because of this, I have stretched more than I wanted. Okay, just a second. Sorry.
No worries.
Okay, sorry about that. They wanted to change something in the apartment. Anyway, so I was saying that if someone needs to go, just feel free to go. And if someone notices that it's going to be empty, just let me know. But don't worry. Okay, so we'll go slowly about. So there was this this understanding of the Poisson Sigma model on a square in a particular way, but it's not so clear how to relate these things to this star product picture, in which you have a disk instead of a square with this particular insertion. They are called insertions at these 3 points, and you see that this computation that we just did point out that to a different function. It depends on these insertions as well. So this is what we are going to kind of clarify in the end. But also, if you are only interested in let's say, Poisson geometry, we will be dealing with a particular way of integrating the Poisson manifold into a local symplectic groupoid using maps on the disk. That's what we're going to do. So just to summarize the main result is this. If you take a coordinate Poisson manifold, so remember that we had this system of PDEs, which are the critical points of this A prime. So I will write this in a second, but the theorem will say that you can always solve this. And not only that, but the disk with these 3 marked points will correspond to a triangle. Sorry, I want to draw it like this. So this disk is of infinitesimal nature. So it lives on the algebraic disk. And this triangle lives, it's a groupoid triangle. So it lives in a particular integration of this Poisson manifold that I call canonical integration, that I will remember in a second. And these are the triangles. So this is one part of the result, that you can always solve this and understand geometrically what the things are. And the other thing is that if you actually do what we were thinking of doing, taking this functional A prime, restrict it to a solution, this defines a function of the parameters. So remember that P1, P2, and little x, they enter as parameters in the computation. So they will also enter as parameters in the PDEs and so on. So this function of the parameters defines a generating function. So actually, there is one function that defines all the groupoid structure that integrating MPI. So let's say from a Poisson geometric point of view, the upshot is to this construction identifies a particular way to encode all the local groupoid structure by using maps on the disk. This is what I'm. So maybe I'll just write this.
Alejandro.
Yes.
Question. So could you say again what the word generating function means here? How
yes, I'm going to define what these things means in a second, but just so in a symplectic groupoid, the graph of multiplication, it's a Lagrangian, right? Like this. The bar means opposite symplectic structure. So a generating function is such that actually this graph is it's an exact Lagrangian. It's given as, the graph of ds. I don't know. There is something, I will write an explicit formula for this in a second, but the idea is that the generating function is a function such that this Lagrangian becomes exact with respect to that function. This is the idea. I will define this more properly in a second.
Do you mean this in like the infinite? So in general, G is not necessarily the cotangent bundle of something, right?
Yeah, well, G will be an open subset in the cotangent bundle.
Ah, okay.
And because something that we will use, you see this P1 and P2.
So this is like a local symplectic groupoid.
Yeah, it's a local.
Okay.
Yeah. It's always local symplectic. Yes. You can think, if you have a local groupoid, it's just a neighborhood of the identities. And actually, this neighborhood of the identities generates everything in the integrable case. So we are not missing that much, actually. So the moral, well, the idea of all this is that describe a local symplectic groupoid structure integrating m pi through maps on the disk. Oops. These maps x eta on the disk. And the functional A prime. Okay, so let's see what comes next. So let me tell you more precisely, without the heuristics, what this functional is and what are the critical points of it. First of all, the functional, remember that here m, or let's say m pi is a coordinate Poisson. Actually, this part, as I mentioned, could be defined for any Poisson manifold, doesn't need the coordinates, but this part, it does, because we are using these linear functionals, P1, P2, P3 functions. So this is the A prime that appears from our heuristic considerations. So there is this part that the critical points of this leads you to algebraic maps on the disk. But now there are these other terms. So these are, let's say, singular terms. This is Dirac's delta distribution. So when this map is continuous, for example, you're supposed to evaluate the map on that point. So when you take critical points of this whole thing, it won't be just algebraic maps, right? Because there will be terms that come from these singular parts. And this will be the interesting thing. So if we do critical points, we arrive to this system of PDEs. Let's say I will call this PDEs depending on pi. And they also, in this formula, P1, P2, P3, and little x, sorry, this depends on P3. So P1, P2, and little x enter as parameters. So these are P1, P2, little x parameters. You can think of them as fixed or given parameters. So this is the system of PDEs, and we will see in a second a particular case in which we solve this explicitly and see what is going on. But let me say quickly, so there are these 3 points where their singular terms are supported, Z1, Z2, Z3. And if I take a sub-region here, for example, then on this region, these terms are not there, right? Because the deltas are supported on these 3 points. And then the first equation together with the second one tells you that you actually have an algebraic map defined on the tangent. Let's say that I call this region R. So you have an algebraic map into the cotangent algebraic. And then there is these two can be understood as boundary conditions. This eta one form, if you take a vector tangent to the boundary, it vanishes. And this big X has to be such that, well, essentially its value here has to be X. So these are, you can think of them as boundary conditions, or boundary conditions. Okay, but then what is, if we want to solve this, we need to understand what is this telling us about the behavior around these points, right? So this is the key point of this system. that these terms here, they are telling us something about this algebraic map. And this is what we are going to do in more or less detail. And yes, so if I repeat this, let's repeat this drawing. So I have this point Z3 here, Z1, and Z2. Remember that letter Y. So I'm going to draw a letter Y here. I take a chunk out. And remember that this boundary condition tells me that on the boundary, there is the zero boundary condition. So even without solving this, we know that if I take the region R to be this part without this little disk, what I will see is this A1, oh, sorry, A2, yes. And let me orient this like this. And A3. So I will have three algebraic paths if I restrict the solution to this little arc or whatever. It doesn't have to be little, but, and because of what I said before, this diagram is like a letter Y. So if this represents a groupoid element, this another one, the third one will be the composition of the two, right? So even from the outset, although we might not know what this means analytically, but what we do know is that this will be given as, that's why I was calling this singular homotopy, letter Y homotopies, that the solutions to this system should be given as a particular way to represent cotangent homotopies, representing this idea that the homotopy class of A3 should be the multiplication of the homotopy class of A1 with homotopy class of A2. This is the point of it. And that's why this system and everything that has to do with this, it's ultimately related to multiplication on some groupoid. That's the whole point. And one last remark that I put here, yeah, just square it with gray. When you, as we will see in a second in this example, we will see that this map X is actually discontinuous at this point. It's actually, it has jumps at these marked points. They correspond to the idea that, for example, this is at this point that I'm marking here, it's the source of an arrow, and at this point is the target of an arrow. So if I go along the boundary, I see source, 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 jump, target, right? So what I want to mention is that if X is discontinuous, it's not clear what this thing means, right? Delta applied to a discontinuous function. You cannot evaluate it at that point. So you need to choose an extension of this distribution to discontinuous functions. And I choose this particular extension. And what I do, I mean, this is a formula, but what I do is exactly what is in the drawing. I take a little arc of radius epsilon. So let's say green. So a little arc of radius epsilon. I average X along this arc. So that's this integral. And then I take the limit epsilon goes to 0. If the function was continuous at this point, then this average tends to be the value of the function at that point. But if not, it's an avatar of the delta, an extension of the delta distribution. And just for you to have an idea of what's going on, if you have a function of one variable that has a jump, one possible way of extending delta is to choose the midpoint in the jump, the average point. And this is what is going on here, but in a particular way using these polar coordinates, if you want. Okay, so don't worry, we are not so far. I want to describe to you in some detail the particular case in which the Poisson structure is constant. So here, in general, you will have a matrix, but now this matrix is constant. It's a constant Poisson structure in Rn. The thing in this particular case, if we go back to this system, you see these derivatives that appear here, they are all zero. So we only get this equation, say d eta equals minus p1 delta z1 minus p2 delta z2 plus p3 delta z3. And we also have the boundary condition. And from this is very clear that this system, it's underdetermined. It will have many solutions. If there is one, there will be another one. Here is clear because if I have one solution, I just sum an exact one form to eta, and it will also be a solution. So to fix ideas, I will supplement this with what is called gauge fixing condition. So, and this is not needed. I just want to single out a particular solution. So if I add this extra equation, then this system has a unique solution, right? Okay. So let me just tell you something. Just from the outset, we see that there is a direct connection to the groupoid structure. If you think of how to integrate this Poisson manifold, it's very clear how to do it, and it involves addition of covectors. You can think, for example, of the case pi equals 0. And you see, if I integrate on both sides of this equation over the disk, so here we get minus p1 minus p2 plus p3, but because if I use Stokes and the boundary condition, I get 0 on the left. So a necessary condition for the solution to exist is that P3 is fully determined by the other two, and this, in this particular case, is the sum. So we just see that emerging directly from the system of PDEs, the groupoid structure is already there. I'm just saying that addition of P1 and P2 is exactly it gives the groupoid structure in the integration of this guy. But let's go more specific. So this is a necessary condition. Let's see what solutions look like. And this is what I plotted here. So I think of eta, let's say, think that particular case that M is just R for simplicity, then the Poisson structure is 0. So eta can be seen as a vector field. On the disk. It was a one form, but you know, on the disk, the Euclidean disk, I can identify one form, some vector field. So there is this particular solution that I wrote here. Well, it's not, let me see. I'm going too slowly, but so this is, let's say, a particular vector field on the disk. It satisfies this property that or let's say one form on the disk, whose derivative is, in the sense of distributions, the derivative of this is delta minus this volume form. So using this, you see that the solution of this whole system, let's say S, the solution of S can be written in terms of these particular one forms like this. It's minus P1 eta supported at Z1 minus P2 eta supported at Z2 plus P1 plus P2 eta at Z3. And so what I did here is to take this expression, here is written in terms identifying the plane with the complex plane, but this is just a real one form. And I plotted it. So the let's say the flow lines of this vector field. And it's like this. If anyone remembers like physics 2 or so, this behaves like a magnetic field, and these points, which are Z3, Z1, and Z2, are as if they were current lines, like a electric current going away perpendicular to the plane. So if there was a current perpendicular to the plane in this point, it will generate this magnetic field like this. And the similar thing happens with these two. The intensity of the electric current is different. It's given by P1, P2, and this sum. But okay, the P3 has to be these two, so that the magnetic field is always perpendicular to the boundary. So this is a very explicit solution. This object already appears in the context that I'm discussing, and it's called Kontsevich propagator. Although it appears in a slightly different form, it has the same kind of origin. So this is what it is. And so let's go a bit further. So far, we understood more or less that there is an actual solution. Even though there are these deltas, we can solve it. And this object is this eta, it's a well-defined smooth form away from the punctures, right? So the fact that this is singular, it only tells you that you have to remove those points from the domain, but outside that domain is completely smooth. So we can go further and actually, okay, there is one extra property that I want to highlight, that if you take this expression and you look what it looks like on an arc of radius epsilon around one of these points, you have this behavior. So theta is the angle coordinates. So there is a point here, let's say Z0. You take polar coordinates. So there is theta here, and the radius is epsilon. So the way this eta behaves, or these guys behave around a point, is like this: is the differential of the polar coordinates plus things that vanish when epsilon goes to 0. And this is a key point, because let me say it quickly. If instead of imposing this, I impose some other condition to fix uniquely the solution, well, I will get a different field, like in the middle, it could do some crazy things. But the behavior near these points, it will have to be like this. So this is a key equation. What this equation is telling us is how to translate the deltas on the PDE into, let's say, estimates on gamma, or behavior of eta near the marked points. for this particular solution, you can verify it directly by direct computation. In general, you expect this because this is exactly, let's say, d of d theta as a distribution is the delta. So this is why this happens. Anyway, so let's move on. Just one more thing. So now what happens to the other field, x? So solving for x. So one of the equations in the system, let me go back to the system here, is this one. So if you already have eta, you have to solve this for x. Y is constant, so you can just solve this equation by integration, like direct integration. And what you get is this, that if you take any path, let's say you mark a point, there are these Z3, Z1, and Z2. And so then I can take any point, for example, this one. And if I want to know x at a point Z, I take some path going from here to here and perform this integral. The path that I chose, it won't matter because eta is closed in the interior. And if you massage this a bit with the particular definition of eta, you'll see that that, as I said before, this x has jumps at these z's 1, 2, and 3. The jump is exactly controlled by pi and the intensity of the current, if you want, at that point. So here k is 1, 2, or 3. Well, actually, what you can check using this and the boundary condition is that if I restrict x to the boundary minus the points, this is a locally constant map. So, well, yeah, it has zero derivative, but it takes on this interval, it takes some value. On this other one, it takes some other value. And on this other one, takes some other value. And the jumps between these three values is exactly given by this formula. So finally, well, let me skip this for a second. So this is what you get for x. You can actually take, for example, that expression for eta and solve for x explicitly. And what you find is this, that x actually spans a triangle. So let me repeat this. There are these three marked points. And in between, there are these arcs. So this whole arc, for example, goes to this vertex because it's locally constant, goes to this vertex. So this is, let's say, V1, and this goes to this vertex, V1. This part goes to V2, goes to V2, and this part in the bottom goes to V3. Remember that the map X, so this is X, is not defined at those points. These are punctures. Yeah, I should have given them names, but so they are the Z1, Z2, Z3. They are punctures. The interior of the disk goes bijectively into the interior of a triangle. And this triangle is Euclidean, actually, in Rn. The vertices, we can compute explicitly what the vertices are. They are like this. They depend on little x. And remember, there was a certain boundary condition like this that depended on little x. So this fixes the triangle where it stands there. The whole triangle, because of the formula, it's actually in a symplectic leaf of this. But because this is constant, the symplectic leaves are affine subspaces, right? So this condition tells you which of these affine which leaf you are. It's the one that contains, well, these objects here, but let's say it's fixed by X. And then well, this I'm telling you about the interior. The interior goes to the interior. The limit, if you come from the interior and you go to a boundary point that is not marked, not punctured, you are going into one of the vertices. But if you do something like this, if you take a path from one boundary component to the other, you get a map like this. Well, B1 to B2, sorry, it would be like this. And the interesting thing that you can verify directly is that if this had radius epsilon, then this path tends to be the edge of the triangle. So what is going on in this particular example is that we have a very standard Euclidean triangle in a symplectic leaf. It's only that it's parameterized by a disk in this kind of weird way somehow, because it sends parts of the boundary to the vertices, and you only get the edges in a limit in which you take this arc to be smaller and smaller. So yeah, just to maybe summarize and finish, what happens here in this example of pi constant actually happens for any Poisson structure. So just for, let's say, 5 more minutes, I was planning to give you some details, but okay, as I said, sorry, lost. I repeat the picture that I had before. So what does this all mean? So this system of PDEs determine this X eta. And if you look at this letter Y, that is, for example, in this region R2, this is a letter Y. What it's telling you is 2 things. That, first of all, associated to each of these gammas, there is a groupoid element in any integrating groupoid or local symplectic groupoid. G2 and G1. So these are groupoid elements. The fact that this can be filled by an algebraic morphism, because we are away from the singularities, it tells you that G3 is the multiplication, multiplication of G1 and G2. And from the example, we learned something more. So what are these G1, G2, and C3? The key point is that the PDE that has these delta terms, PK, delta ZK, they actually tell you what the groupoid elements are. So this G1 is determined by P1, this G2 is determined by P2, and G3 is determined by P3. And because of this relation, these 2 actually determine P3. Before we get that it was the sum of these 2, but in general, it's something more complicated, it's nonlinear. So this is what is going on. So again, I repeat, it's a particular family, if you want, if you think of epsilon here, an epsilon. It's a particular family of letter Y homotopies which becomes singular at these points, but the particular way in which they become singular at those points actually determine the groupoid elements that you are going to multiply. That's the point. So, okay, just to maybe answer questions that were raised before. So if you have a coordinate Poisson structure, coordinate Poisson manifold, there is a canonical integration. Local symplectic groupoid that I will be denoting G sub pi. I will describe it very quickly. This comes from the work of Karasev. So first of all, you define the source map. So the source map is defined on a neighborhood of zero section onto M by this relation. So here the parameter P, that is the covector part, is supposed to be small. So this relation defines uniquely this guy, or at least the germ of it, around zero, just because when P equals zero, this is satisfied. Well, let's say alpha pi will have this structure. It will be X plus something of order P. But in any case, using the implicit function theorem, you can verify that this defines a smooth map. And Karasev verified actually that it's more than a smooth map. It's a realization map. So it sends the canonical symplectic structure, or symplectic brackets, into the pi Poisson brackets. So this is an example of symplectic realization. And it's moreover what is called a strict realization, because if I take the zero section here, it's a, as you see from this formula, it's a section of the map. And the zero section is Lagrangian here. So this is called a strict realization. So now if you follow, for example, the construction of Coase, Dazord, and Weinstein, you know that a strict symplectic realization defines uniquely a local symplectic groupoid, such that the realization map is the source map. And for example, if you want to recover multiplication, you can use it by Hamiltonian flows. So these are Hamiltonian flows on. So let's repeat. If I have a function on M, I pull it back by this alpha map, and I take the Hamiltonian flow. And the point is that the multiplication is such that this is a right invariant flow, as it's, well, sorry, left invariant flow, because it's the source. If I use the target beta, then it would be right invariant. In any case, so from this you recover all the structure maps. In particular, in this particular example, this formula has certain properties that imply that the inversion is just multiplying by -1. Okay, so there is this canonical integration. This is a local symplectic groupoid, meaning that all these maps are defined in neighborhoods like this. So let me go skip this for a second and tell you something quickly about generating functions. So what is a generating function? Here we will be needing the following. Suppose that we have a groupoid like this, that it's given by an open subset in the cotangent bundle. I'm thinking that M is coordinate again. Suppose that the identity is just the zero section. So this is a neighborhood of the zero section. And also suppose that the symplectic structure is the canonical one. So for such a local symplectic groupoid, and again, here M, it's a coordinate space. A generating function is a function like this. It's defined on, let's say, T star, two covectors over the same point. And this, I denote these two covectors over the same point by P1, P2, which are the covector parts, and X is the base point. And generating means that the multiplication, the graph of multiplication is given exactly by this formula. So here there should be some x1, but this x1 has to be the partial derivative with respect to the first parameter. Here there is an x2, again, it has to be the derivative with respect to the second parameter. And here there would be a p3, let's say, that it has to be this derivative. So because M is coordinate, I'm using implicitly that this is M times the dual vector space. And you can check that such an object, for any function S, this defines the Lagrangian submanifold here. Now, not every function will define a local groupoid structure. There are axioms like associativity and so on. And then these axioms become equivalent to a restriction on the function S, which is called the symplectic groupoid associativity equation. This is introduced in a paper of Cotangent, Theorem, and Felder. So I repeat, if I just take some random function, I take this Lagrangian, and I want this to be the graph of a groupoid, local groupoid structure, then the axioms become equivalent to this equation. And this is what I want to highlight about this equation is that it's quadratic because, for example, x bar here, it's actually a derivative, it's a nonlinear PDE. There appears partial derivatives of S inside a quadratic S. In this paper, they provide a formal family of solutions, but what we can show, this is in this draft that I'm writing that had all these things that I'm telling you about, is that this canonical integration of Karasev always admits, doesn't matter what the Poisson structure is, always admits a generating function. We actually have a formula for it. And if you had another one, it has to coincide with that one as long as it vanishes like this. So it's uniquely determined up to additive constants. So I hope this more or less clarified what the generating function is. It's really a function that generates everything. So then to put everything together, yeah, let me go just one more minute. So remember that the theorem, the main theorem said the following. If I take, well, let me say something quickly. I mentioned family of solutions of PDE. Remember that these were parameters of the PDE. So a family of solution is a smooth assignment for each parameter. And we only care about small parameters, so close to, let's say, 0 times m. So in a neighborhood of this lies inside m star times m star times m. So for each such small parameter, you have a solution. And I didn't say, but a solution can be made very precise in the sense that in the puncture disk, where you remove those 3 points, it's just a infinity function is infinity one form, collection of one forms, and blah, blah, blah. Sorry, this is P3. So this is a family of solutions. I would call them strong because they are not distributions, they are actually functions. So once you have such a family, and remember the system was underdetermined, so there could be many families. But whatever, you take any family that you like, and you can define a function from this. This is the SP. Because we do exactly as the heuristic considerations told us. I take the functional and I evaluate on the corresponding solution. So this solution is the solution corresponding to those parameters. So in a sense, what we do is this. I fix certain parameters. I produce a disk somehow with this PDE, and then feed this disk into the function. So this produces a number. And the key point is that, sure enough, this guy, as the heuristic tells us, this guy is a generating function. For this canonical integration. I just outlined here very quickly. We already know more or less that, I mean, you can prove this rigorously, but I'm just doing a summary. This P3 guy, it has to be this just because this other function S pi that comes from independent considerations is a generating function. And also, if you compute the partial derivatives of SP defined like this, then you use that these guys were critical points of this. So many, when you apply the chain rule, many terms vanish and you only get this. Okay, I won't give more detail, but in a sense, you can prove this to very high level of detail. And let me just finish with these triangles that I didn't mention. The proposition says this, that, okay. Okay, let me say this very quickly. If I have a solution, the idea is that you can integrate it. This is some sort of singular algebraic morphism, and you can integrate it into a, in principle, singular disk in any groupoid integrating m pi. In particular, we can do this for the canonical integration. And the key observation that goes pretty much as we saw in the concrete example is that this disk is actually a triangle. So the interior of the disk corresponds to the interior of the triangle. And those little arcs around the singularities correspond to paths that tend to be the edges. And this thing actually establishes a one-to-one correspondence. So all solutions actually come from triangles. You can show this by playing a bit with the PDE. And just one more remark, that the edge here is not a straight line in the Euclidean sense, but it's a right invariant flow. On the groupoid generated by the P's. For example, this would be generated by P2, this one by P1, and so on. PKs that can be seen as sections. So I take one of these P's, I think of it as a section of the algebroid, I take the right invariant flow, and this generates this blue line on which the other accumulate. But the thing is that this limit is regular, so you can actually extend it to a map from the triangle. That's another point, that the singularities of this guy are only singularities of the parametrization. They are not geometric singularities. It's not that this goes to infinity or something. Okay, I finished with this. If someone wants to ask some questions, I will leave it to the these parts for the questions. Thank you. Sorry for going over time.